Okay, so just picking up where we left off here. Okay, so it does do some review. We don't have to define the total differential too well. When we kind of read through the text, they do say it a little more elegantly. It's hard to understand, but it's just basically the simple understanding we did in the previous video. But let's just kind of see how they describe this here. So finally, we want to know how marginally changing variables x1 and x2 at the same time affect y. For a function y equals f of x1, x2, the change delta y resulting from small marginal changes delta x1 and delta x2 is approximated by the total differential. Yeah. It has an intuitive interpretation, just like we described in the last video. I just basically see it as y equals mx2 of them, which essentially is what it is. For small changes, delta x1 and delta x2, the total change delta xy in the dependent variable is approximately the sum of the effect of each change in the independent variable. So we are changing x1 by delta x1, and this has a marginal effect. You see, they state a partial derivative, and all of us, we have no idea what it means, but this is how they describe it. So we are changing x1 by delta x1, and this has a marginal effect on the slope. On y, hence the term that captures the change in y incurred because of the change in first variable. While the other one, the exact same thing, except for the other one, we always kind of say it very informally, but the first one and then the second one, uh, sorry, captures the change in y incurred because of the change in the second variable. So the table below summarizes the derivative rules that we will use throughout this book. So we kind of jump around. We're basically going straight through, but when we did some of the chapter 2 homework, we're still in chapter 2. But when we did a little bit of the, what do we say? We're doing multivariable functions, and calculus 1 was a single variable functions. But so these three here are just derivative review, which we already did. We're not going to talk about this. And these are two of the most common multivariable functions in this course, two of the easiest ones. They're very easy. This is one, this is one. This is the, as we know, we just did this now, previous video. This is the Cobb Douglas, yes, that one right there. But so we have three derivatives, and then we have partial derivatives. In examples, we don't have to go over that because we basically already did that. So that's it, incredibly easy derivatives for this entire book here. Okay, so this is very good. Any very simple understanding is good. We have 3D changed to 2D. If you look at 3D, three-dimensional from a bird's eye point of view straight down, then they have the contour lines. The contour lines on any map are actually really cool. The contour lines literally just trace out all points that are at equal elevation. So most people can understand a contour map fairly well. So 2.2 level curves. At some point in grade school, you learn that a 3D mountain can be represented by a 2D topographic map with contour lines. Each contour line in the map connects the points on the mountain with the same elevation. Topographic map with contour lines. We can use the same idea to represent the 3D graph of the function in a 2D graph, figure depicts, etc. So we don't have to go through that. What they do is they introduce this right here. Yeah. Let's quick denote what they're doing here. This is how I understand this. So we want to kind of pause. So this is a 3D function. If we can see there, that's the XY plane. So we're going to erase this, but we have the XY graph. But here it's going to be X1 as a function of X2. And then we have the Y graph coming straight out of the page towards us. That doesn't really work. So you tilt it on its side. And we have X1, we have X2, and then it's not calculus 3. It doesn't matter if we call it the Z, we never do. We would call it the Y, the up, the vertical as a function of X1 and X2. So it's a kind of a three-dimensional graph there. Yeah. So that is the graph of that right there. It's Y equals 4x1 plus 8x2 represents that. Okay, so this is going to be, we know this, but this is x1. This is x2. I know that I just wrote that, so we're going to erase that. If you look straight down on the graph, I think this is pretty obvious, but if you look straight down from a bird's eye view, then this is it's three-dimensional, but this is looking straight down. This is the 2D contour map. So we know that there's elevations that all have the same slope there, yes? Elevations. So all of these, this whole line is at a single elevation, single elevation, single elevation, and it's curving like down. Yeah. And then we do this right here, but they just depict one line. Yeah. So let's just kind of see what they're doing. We want to kind of know what that means, but that right there is basically it. So for example, what are all combinations of, they do this thing here. They want to introduce this basic idea. Yeah. So they're going to do it right here. If we have y equals 4x1 plus 8x2, you can set y, the height, equal to any elevation like 80. Yeah. Equals 4x1 plus 8x2. Let me kind of do it right now. I'm just going to start over a little bit where I solve it and then I read it. I'm just going to do what's in this circular thing here, but they break it down to a y equals mx plus b. Yeah. So if you have any kind of easy or complicated graph, when you look at it down 2D, we're just going to derive, yeah, we're not going to have circles or anything, but you derive the two-dimensional levels. I'm not sure what to call them. Yeah. So all they're going to say right here is if we have the graph y equals 4x1 plus 8x2, yeah. So we can do 60, we can do 80, we can do anything. We want to isolate all points that are at height y equals 80. So we just do that. So we obviously skip the algebra. Yeah, skip the algebra, just divide everything by 4. Yes. So we want it correct as all y equals mx plus b. You could write it backwards with x, but we want it to equal the vertical axes there. What does that mean? That would mean that we're solving for x2. So we have like 2x2 equals a negative x1 plus 20. Yeah. So do we kind of have it there? Divide everything by 2. It's kind of like a simple homework problem. It's too easy. Why are we doing it? Okay, so it doesn't matter the language they write it in. We kind of have that little thing right there, yeah? So if we have the graph, him, you just set it equal to whatever elevation, yes. And then you set it equal to whatever elevation, and then you get a graph, a two-dimensional graph, which is going to be the contour line for everything at that elevation, yes. Okay, so let's kind of read on here. So for example, what are all combinations of x1 and x2 that yield y equals 80? We just did that. So we're looking for all pairs, etc. And then they kind of do the little outline right there. Yeah. Note that in the original function f, we have y as a function of x1 and x2. When we fix a particular value of y, we can construct a new function. They say a lot about, we're going to kind of skip this here because we don't need it, but they say a lot that you have this function x2, it's like a trade-off, as if it's like a complicated thing. We can pause the video and we can kind of read on. I'll just kind of slightly scroll down so we can see that. But they just, I've kind of read through this and they just do this big complicated thing where, if we increase something a little bit, we have to decrease something so that we stay at the same value y equals 80. Yes. So all they're saying basically is that there's the set of all points such that y equals 80. We could read through this if we want. I don't find it particularly important here. We're just going to skip to this place here where it says 2.2 in the next video. Yeah.